Hello everyone, my name is Abhijit Gupta and today I'll be taking session on transient heat conduction. So in the earlier chapters we have seen steady heat conduction. So let us focus from now on transient heat conduction. In the real life most of the problems will be related to transient only. So it's very important to know what does transient heat conduction mean. So heat transfer due to conduction is varying with time. Now, to start with, let us go back to a general equation of heat conduction. Let me write it again. So where capital T means temperature and small t means time. Now if you all remember, in our earlier chapters we haven't considered this parameter at all, because in steady we have always taken that dou T by dou T is equal to 0. That means no parameter changes with time. That means in earlier chapters, in steady heat conduction, we have always assumed temperature is varied with only position x, y, z. But for today's class, we should look into transient as well. So for transient, we know that dou T by dou T will not be equal to 0. That means the temperature changes with all the three positions x, y, z, and as well as time t. So t is x, y, z, comma t. So as we have developed in our steady heat conduction, we have simplified the problems into 1D to get the analytical solution. Let us do similar thing here as well for transient heat conduction. So for this, let us take a simplification. Let me tell this as first case, where temperature is only dependent on time, only on time, and this analysis is called as lump system analysis. Now what is this lump system analysis? So for explaining that, why we are calling this as lump, to explain this, what I'm going to do is I'll just take one example. Let me take a ball. There are a lot of positions in this ball, but I'm showing only some of the points, and I'm specifying the temperature on this ball as 70 degrees centigrade, right? So if you notice, this ball is considered to be lump. That means all the temperatures, interior temperatures, remains uniform across the complete ball. So there is no change in the temperature across x, y, z position. So T equal to 0, let us assume this is a temperature of the body, and at T equal to delta T, that means after delta T's time, the ball, let us say this ball is heated up. So these temperatures are again so now if you notice, the temperature of this is ball is 80 degrees centigrade. So that means all the coordinates, the interior temperature of this ball now are at 80 degrees centigrade. Again, if you look at it, the temperature is not changing with x, y, and z. That means the interior temperatures of the ball remains uniform at all times during this heat transfer process. The temperature is only changing with time, and that is the reason we call this as lump. So body is considered to be lump whose interior temperatures remains constant during all times. So the temperature, the body temperature remains constant irrespective of x, y and z. That means temperature is not changing with x direction, temperature is not changing with y, temperature is not changing with z, temperature is only changing with time t. And this is called a lump system analysis. So in this session I will be focusing only on lump system analysis. Now let us derive an analytical solution for this. Let us consider an arbitrary shape body. We always assume the arbitrary shape in the sense amoeba, right? So let us consider a solid body of any arbitrary shape, something like amoeba, whose mass is m, density is rho, volume is V, surface area AS, specific heat C. So this is solid body is at MV AS with rho. And let us assume the initial temperature of this solid body is equal to TA. Okay guys, so we have defined all the parameters for this solid body which are required for this analysis. Now let us keep this body in an environment, in an hotter environment, let us say, with T infinity temperature and heat transfer coefficient as H. So I am keeping this body in a hotter environment. That means the T infinity is greater than Ti. So for this analysis, note this analysis is also valid for T infinity less than Ti. That means if you keep the body in a colder environment also, this analysis is valid. But for today's session I will be taking that the body is kept in a hotter environment. So logically, as the time progresses, body gains the temperature. But let us find the analytical solution for this. So during time dt, what happens? The body gains temperature, right? That means temperature of the body rises by some differential amount, say dt. So this d capital T means change in temperature, d small t means change in time. Now let us do the energy balance. What happened in this differential time dt? What happened, guys? The heat transfer from environment into the solid body during dt, that is heat transfer into the body during dt is equal to, what this should be equal to, guys? The increase in the energy of the body during dt, right? Increase in the energy of the body during dt. Now, what is the heat transfer into the body during dt? It is taken by Newton's laws of cooling, right? Which is HAS T infinity minus T during time dt should be equal to mCp change in temperature dt. Let me take this equation 1. Now we all know that m can be written as rho v, that is mass is equal to density into volume. So let me substitute this in this equation. And let me write this equation as 2. So let me rearrange this in such a way that variables are separated. Now we all know when time t is equal to 0, the temperature was initial temperature, which is Ti, and at any time t, temperature is T. Of course this T would be a function of small t because it is changing with time. Now let us integrate from 0 to t dt is equal to this rho v Cp and Ha are constant. So this should not come under integration. So 0 to t dt is equal to rho v Cp by Has integration of dt by t infinity minus t from Ti to t. Making sense, guys? Now let us integrate this. What is the integration of this? 1 dt t rho v Cp by Has ln of t infinity minus t from Ti to t, since integration of 1 by dx is ln mod x plus c. So from this we have done this, right? Now integration of this dt divided by t infinity minus t. So there is a negative sign associated with there is a negative sign associated with t. So it would be divided by minus 1 from our 12 standard integration techniques. So far so good. Now so the integration of 1 dt is t, so let me write the limits as well again. Now when I apply these limits here, what happened, guys? The limit, it would be t upper limit minus lower limit. So t is equal to this minus sign here, so this will be minus rho v Cp by Has. Now upper limit minus lower limit, that means ln of t minus t infinity divided by Ti minus t infinity, right? So let me write this as equation number 3. And so if I apply this limit, it would be ln of t infinity minus t divided by t infinity minus Ti. I can take negative sign common on both numerator and denominator, and then we'll get this ln of t minus t infinity divided by Ti minus t infinity. Let me rearrange this again. So let me rearrange this. How will this look like, guys? Minus Ha t divided by rho v Cp is equal to ln of t minus t infinity divided by Ti minus t infinity. Right? So, and let me take this as equation number 4. Now let me take this ln on the other side, and then it will become e exponential, right? So t minus t infinity divided by Ti minus t infinity is equal to e minus, so is equal to e power minus Ha by rho v Cp t. Let me take this as equation number 5, and this is a temperature distribution over time for lumped system analysis. Now let me take this rho v Cp by Ha as some time constant tau. So this is surface area HAS, right? Suffix s. Okay. Now this equation, how will it look like? T minus T infinity by Ti minus T infinity is equal to e power minus T by tau. This is the analytical solution. Now you must be thinking why I have changed this rho e Cp by Ha as tau. What would be the units of tau? It should have the same units of time, right? Because these are numerator and denominator, according to units and dimensions, tau should have the same units of time, which is seconds. Or else we can find the units of tau using this also, rho e Cp by HAS. It will get back to seconds. Now, how does it helpful? What are the uses of this? Why we are using it? Why we are giving a new name for this tau as time constant? Because this has a very great significances. So for that, let me do something. Let me draw a graph of this analysis. Temperature, time. So the body was initially at T equal to 0, it was the temperature was Ti, right? And the temperature of the environment was T infinity, right? Now let me consider there are three bodies with some tau 1, tau 2 and tau 3. Let us assume there are three bodies randomly with different material properties, tau 1, tau 2, tau 3, such that tau 1 is lesser than tau 2, lesser than tau 3. So if you plot it here with some values with this tau 1, tau 2, tau 3, and if you plot a graph, we will get something like this. So body is getting heated up with time, but it cannot go beyond the environment temperature, right? And then this is for tau 1. Let us take for tau 2, second body. Tau 2. Let us take for the third body. Tau 3. So if you notice, all the bodies are coming to temperature T infinity because that is the environment temperature. It becomes asymptote here. Now what we have noticed, one more thing is, the first body is getting heated up faster than second body, and then second body is getting heated up faster than third body. That means lesser the value of tau, faster it gets heated up, right? So what all we learned from this graph, guys? The first point is, lesser the value of tau, faster the body gets heated up. Second, the time required for a body to reach some temperature T, right? So for example, if I want to understand how much time is taken for a body, first body, to reach this temperature, then we can extrapolate it, right, using this. So we can identify the time taken for this body to reach some temperature T, and this temperature plot approaches to T infinity exponentially because the solution looks in terms of exponential, and initially the temperature changes rapidly. It's heated up, it heats up rapidly, and then it becomes slow. The process becomes slow. That is the tendency of exponential curve, right? So these are the points which can be the outcome from this graph, and this is the significance of time constant, that lesser the value of tau, faster it gets heated up. Now this equation number 6, it's very important to understand the temperature distribution. Now let us say we want to find the convection heat transfer. Let us say we need to identify the convection heat transfer between body and environment at that particular time, so say some time t. Then it would be Q of T, right? And it would be similar. Newton laws of cooling, just write HA T infinity minus T of T. So for example, if you want to find the heat transfer, convection heat transfer between the body and the environment at that time, say 5 seconds, then this Q would at 5 seconds would be HA T infinity minus this T would be at 5 seconds. So we have to evaluate this T, evaluate this from equation number 6, right? So from this we can find at t equal to 5 seconds what is the temperature of the body and then substitute here. So we can identify the convection heat transfer between the body and the environment at that time 5 seconds. Now if you want to find the total heat transfer, this is important. How to find the total heat transfer? Total means summation over all the times. So Q of T, this would be minus HAS T of T minus T infinity 0 to T plus Q total is equal to. Now you must be thinking, where is T here? How would we integrate this, right? How to integrate this? Let me write dt. Now how we gonna integrate this? Because we need to integrate this, right? How to integrate this now? Well, there is no, but we all know that this temperature is dependent on time. So let us write this T minus T infinity as, from equation number 6, it is Ti minus T infinity into e power minus T by tau dt. Now this would be, how much this would be, guys? Minus HAS Ti minus T infinity would be constant, and integration of e power minus T by tau would be e power minus T by tau 0 to T divided by minus 1 by tau. Since integration of e power ax dx would be e power ax by a plus c, right? Remember this identity from our 12th standard. So Q total will be minus HAS Ti minus T infinity into e power minus T by tau divided by minus 1 by tau. Now let us bring it. So what was the last equation which we got? Q total is equal to minus HAS Ti minus T infinity divided by minus 1 by tau e power minus T by tau 0 to T. Now what is tau? Rho Cp by HA, right? Let us substitute that. Minus and minus become plus. What would be the value of this, guys? It would be e power minus T by tau upper limit minus lower limit. So e power 0 is 1. Since e power 0 is equal to 1. Now let me write this Q total is equal to rho e Cp. Can I write this Ti minus T infinity as T infinity minus Ti with minus sign and e power minus T by tau minus 1. We remember that rho v can be written as m. So since m is equal to rho v, right? So this is our Q total. What was the previous equation number, guys? Equation number 6, right? So this would be equation number 7. Equation number 7. Now if you want to find the maximum heat transfer possible for this, how would it be? That means when the time t tends to infinity, the temperature tends towards, the temperature of the body tends, it increases from Ti2 towards T infinity, right? It tries to go towards to infinity, and that is a point where we tell that Q total would be Q max. So now Q max would be minus mCp T infinity minus Ti, and then this T limit should tend towards, T2 should tend towards infinity into e power minus T by tau minus 1, right? So when T tends towards infinity, e power minus T by tau tends towards 0, right? Because it becomes 1 by e power T by tau. So the numerator will be infinity, so 1 by infinity would be somewhere near to 0. So this Q max would be minus mCp T infinity minus Ti into minus 1. So Q max would be mCp into T infinity minus Ti. So this will be maximum heat transfer possible. Question number 8. So far so good, guys. We identified the temperature distribution, we identified the heat transfer at the particular time, we identified the heat transfer, total heat transfer, we found the maximum heat transfer as well. Now it's very important to understand when can we use this analysis. Can we use for all the problems? No, we need to understand when can we use this, because we have assumed that the temperature is varying only with time. So that was the assumption if we have made at the beginning of this analysis. So we should know when this analysis can be implemented and on what all problems it can be implemented. The first assumption, we all know that temperature across the body remains uniform. That is the first assumption, right? And for that, let me write this as criteria for love system analysis. So to understand this criteria, let me define one number, Biot number. We denote this as Bi, and it is defined as HLC by K, which can be also written as LC by K divided by 1 by H. This K is the thermal conductivity of solid, and H is heat transfer coefficient between the body and the environment, and LC is the characteristic length, which is equal to volume by surface area. Now, what is LC by K? We all know that LC by K would be conduction resistance within the body. This should be equal to convection resistance at the surface of the body. Now, if you remember that example which I have taken, this ball, right? The temperature was uniform across the body. Remember this 70 degrees centigrade, 70 degrees centigrade, right? So that means the temperature is uniform across the body. That means this conduction resistance within the body is very low. It's very, very low, in such a way that the temperature should be uniform across the body. That means the numerator of Biot number should be very low. And how low? So this analysis is valid when Biot number is less than or equal to 0.1. ठीक है guys? Now ideally I know, and we all know that logically the numerator should be 0. That means ideally Biot number should be 0 to use this analysis. But as you all know, it won't come down to 0, it will be very less. So let us take that assumption as Biot number lesser than or equal to 0.1. So whenever the Biot number is lesser than or equal to 0.1, this analysis can be implemented. Okay guys, and one more thing, the similarly we can do this when T infinity is less than Ti, right? So this analysis is also valid. ठीक है? This lumped system analysis is also valid when the body is kept in colder environment. That means T infinity less than Ti. But remember, to implement this analysis, Biot number should be always lesser than or equal to 0.1. So before concluding this class, I would give one example for this, guys. So let us not solve that problem in this class. We'll solve the problems in coming sessions. But let me tell you what does exactly, in what problems you can implement this. For example, let us take one automotive example. There is a brake disc. So as you all know, after keep on applying the brakes gets heated up, and we need to cool down that. So when the brake is rotating in the normal road, so once we keep on applying the brakes, the brake gets heated up, and then suppose the car is in a running mode on the road with the ambient temperature say 35 degrees centigrade, right? So this brakes tends to cool down with time. So this lump system analysis could be very helpful in doing that. But the material of those brakes should be in such a way that the Biot number should be lesser than or equal to 0.1. So this is very important criteria to implement lump system analysis, guys. So by this I would say bye. Have a nice day, guys. See you in coming sessions. This is Abhijit Gupta signing off. Bye bye. Take care.